We are going to talk about the first law of thermodynamics, which is all about conservation of the energy. So, what is thermodynamics? The thermodynamics is the study of the energy and its interconversions. So, it's all about the conversions between the energy, which is called thermodynamics. The first law of the thermodynamics, what does that say? We've already talked about this a little bit in the previous video. So the first law of thermodynamics says that the total energy of the universe is constant. So we do not we do not produce or destroy any energy. We're just converting between the types of energy. Okay, so the first law of thermodynamics states that the total energy of the universe is constant. Okay, so let's talk about internal energy. So we talked about the energy in the previous video. We talked about different types of energy. So the internal energy is the sum of the kinetic and potential energy of all particles that compose the system. Okay, so if you think about an enclosed container, okay, you have some certain amount of gas in the container. They have energy. They have all the atoms are moving. The electrons are moving around the nucleus. If you have nucleus energy, there are different types of energy. Okay, that could be kinetic or potential. The sum of all the energies of all particles in that system is called internal energy. And internal energy, we show it with the capital E, is consists of the kinetic energy and the potential energy. So it's the sum of the total energy of all particles that compose of the system. Okay, so we have to learn also about the term state function. And what is state function? State function are properties that are determined by the state of the system, regardless of how we get there. So if a property is a state function, it means it doesn't matter how we get from point A to point B. What matters is the difference between these 2 points. Okay, that is called state function. We don't care about how long it takes to go to the part B, or what route we take to go to the part B. The only thing that matters is the difference between part B and part A. So let's have an example to get a better grasp on it. So volume, for example, is the state of function. Okay, so if you have 6 ounces of water in a glass, it doesn't matter if how you get to the 6 ounces. It might be just a glass of water and you pour 6 ounces of water in it. It might be 12 ounces and you drink 6 ounces and you get to the 6 ounce. Or maybe you had 3 ounces and it was there for a while, and then you add more 3 ounces. Or you had 4 ounces, you drink some to get to the 1 ounce and you add 5 ounces. But it doesn't matter. What matters is that you have 6 ounces of water, right? So that is called state of function. So state of function is something that it doesn't matter how you get there. What is important is that state. Okay, so the state that the system is in, it matters. Okay, so the magnitude of change only depends on the initial and final. Okay, so you can have delta, and delta is the difference, is the change, and it's a general definition. Delta is always final minus initial, the final state minus the initial state. And it could be explained on volume, on energy, on pressure, on whatever. Okay, so delta is change, and it is the final minus the initial. Okay, so we talked about a volume as a state function. We said that it doesn't matter how you get there, how you get to the 6 ounces. So if you want to find the change in the volume, it's the final volume minus the initial volume. For example, you had 2 ounces of water in a glass, and then you have 6 ounces. That 2 to 6 might be you had 2 and you pour 4 ounces and now it's 6. It might be 2, you add 10 to it and you drink 6 of it and now it's 2, now it's 6. or it can have different routes, but it doesn't matter. You just want the change, and the change is 6 minus 2, and the difference is 4 ounces. Okay, and that's what matters. So the properties which are state function, you can talk about the delta. You can have delta of that state function, and it means the final minus initial. So something that you have to pay attention to is the properties which are state function are abbreviated with a capital letter. You see, we have volume with capital V. We do not write volume with small v, right? Energy, we talked about the internal energy, it was capital E, right? Because it was state function. So the quantities which are state function, we write it with capital letters, uppercase. Quantities that are not state function, we do not write them with a capital letter. For example, work is small letter work, or heat that we're going to learn about is Q, so we use lowercase. If you see a quantity with in uppercase in capital letter, if well, work is not the state function, volume is in capital letter, so that's the state function. So if a property is a state function, we abbreviate it with capital letters. These are some other examples of state function. Energy, we already talked about it. The total amount of energy, the kinetic and potential energy are state function. Temperature is state function, so you can define delta on it. So if you want to see a change in a temperature, so or not even a change. So if the temperature, say it's 75 today, and it doesn't matter how it gets to 75. Yesterday it was colder, yet yesterday it was warmer. No, if you want to see the change, yes, you can see yesterday, and then you can see now, and you see the change. But how it gets there, it doesn't matter. The temperature is 75. Okay, so that's state function. Pressure is also a state function, so you see a change in the pressure, you can define it with delta. So you see these people climbing up the mountain, and the altitude that each person is climbing up, it doesn't matter what route they're taking. These people take the longer route, going all the way through this route and going to the top of the mountain. They're going 12 miles, but the altitude is still the same. So we cannot say these people went up, I don't know, 200,000 feet, but the other group, we choose this route, which is more straight route to go to the top, takes 10, for example, 10,000. No, the altitude is the same. So all of these people going up the altitude of 10,000 feet. Okay, so that is a state function. So if you remember, I said work is not state function, right? So these people for sure had traveled a longer distance, and they're doing more work, right? Because if you remember, work is force times d. The distance is higher, so they're doing more work. These ones, well, they're putting more energy because it might be harder, and I cannot say the work is equal because the altitude is the same. It might be close, it might be less, a little bit difference, but or maybe high, I don't know. But we cannot say anything about it because we don't have enough data. But what we can say is that work is not state function. So these people, they travel a longer route, they might have done more work than the ones that taking the shortcut, if you can call this a shortcut. But anyway, so they have done different amount of work because work is not state function, but the altitude is a state function. So it doesn't matter which route they take, all of these people going up the altitude by 10,000. So we've learned about the first law of thermodynamics. We've learned about that this is all about conservation of energy, that we're not going to produce or destroy any energy, we're just converting between them. We've learned about internal energy, which is the sum of total kinetic and potential energy of all the particles in the system, and we've learned what is state function in this video.